Okay, so we'll continue the discussion about this sputtering process. So you have seen as an accelerated ion impinges on the target, which is placed on the cathode. Okay, and it's placed on cathode because you have then higher voltage drop across the dark space. Okay. So they can be accelerated, right? And as they hit the target, a lot of things happen, and one of that is actually the ejection of the atoms, particles from the surface of the target. So on the substrate side, which is actually placed on the anode, you have a similar voltage dark space and a voltage drop in the dark space, which will also accelerate the ions, right? But not to the same extent as the cathode dark space, because the voltage drop here is smaller. So you have a these particles would actually hit the substrate with higher energy. Yeah. So that has consequences, and in fact you can use it for different purposes. Okay. So the basic idea is that if you have this particles depending on the energy, so this can actually lead to different things. So in this range of energy, about 15 or less than 15 electron volts, these fast particles actually can break surface bonds, right, and increase the diffusion of different species on the surface, and so on and so forth, by transferring energy to the surface atoms and molecules. On the other hand, if you have higher energy, it may actually lead to damage in the surface layer, where they transfer this higher energy. That leads to cascading of displacements. For example, this host material atom. Oh, this is actually the surface layer. So these are pushed inside by the higher energy and momentum of the incoming particles. And larger energies, you can have this thing actually also getting implanted, and atoms from the surface of this sputtering target being ejected out. Okay. But this can happen both on the cathode and anode. Only thing is that on the anode side, the energy that the ions gain would be less, because the voltage drop across the dark space is smaller. So this is actually, the first two parts are very important, but also the later thing is actually made use of in some of the processes. So we will see examples. So you can do many things with this: sputtering of the substrate or the growing film during this deposition, because the ions hitting the substrate surface are also of high energy. So may be useful for cleaning it prior to the film deposition. Yeah. So I can clean the surface prior to the deposition of the film. And different ways that you can do this. For example, this can be just a sputtering using argon. So what in some systems there is a capability that is available to you to just reverse the polarity of the substrate, meaning anode and cathode, right? You have the substrate and the target, and you can actually switch the polarity of the supply, right? And usually done using a switch, and then the substrate during that time becomes your target. Okay, so there is more higher potential drop across that, and as a consequence, you can remove atoms from the surface of the substrate. Okay, so this is can be used for cleaning, So it's called back sputtering. Yeah. Another technique people use is to use a reactive plasma for this kind of purposes for cleaning. For example, if you use oxygen plasma, right? So any organic substances or any material that has a volatile oxide can be cleaned using an oxygen plasma. Okay, but oxygen plasma, you have to be careful in a sputtering system, because if you let in oxygen, the surface of the target, if suppose it is aluminum, can become the oxide of aluminum. Yeah. So then, if it is a DC sputtering system, you have a problem, because that will get charged and so on. And the initial films that you deposit will be aluminum oxide and so on. But I'm actually just mentioning that in plasmas, these possibilities do exist. Change the composition of the composite materials if the sputter yield of atoms differs. So this is essentially if you have a composite material that you want to deposit. Okay, so I make a target of this composite material. But suppose the sputtering yield, which means that if I actually sputter this target with fast ions, okay, let's say the material that you want to sputter contains heavy atoms. Yeah, it will be difficult to sputter them out. Okay, so as a consequence, there's something called sputter yield, which means that you have a certain flux of this ions, let's say argon ions, hitting the target, and how many atoms of the sputtered material comes out, right? So this is called a sputter yield. Okay, so the ratio of this can be thought of as sputter yield. So if some of the atoms are heavy, or they are actually part of larger molecules, very strongly bonded, it may not be possible to get this the same yield for each of the types of atoms on the surface. Okay, so you get this composite material is what you have in your target, but the film that is getting deposited on the surface would have a slightly different composition, because the sputter yield of the constituents of the composite material are different, and as a consequence, what reaches the substrate to be deposited would not be the same as what you have on your target. So in that case, I can actually use some of these techniques that you use this fast particles to create an intermixing. Yeah, because you have seen in the previous slide that you can actually cause cascades of, meaning you can push these atoms around on the surface by high energy particles, right? So there are all these possibilities. And then another technique is actually to use the sputtering process to smoothen out the trenches. Okay, so if you have a trench like this, so you will see that, and I may be able to smoothen out this place so it becomes more open, because sputtering is not necessarily a line of sight deposition process, so you don't have 100% step coverage. Okay, so we'll see that, and I'll show you one example. So this is another possibility. Using displacement cascades, you can create interstitials in the material, which can then enhance diffusion. Okay, and interstitials can, so this is kind of defect generation, can relax strain in some cases, and you can mix layers of deposited materials, and this can be used to avoid phase separations. Okay, so you have different, let's say a composite oxide may segregate into individual oxides. If I deposit, for example, aluminum hafnium oxide, yeah, or hafnium aluminum oxide, it may actually happen that you have hafnium oxide clusters and then aluminum oxide clusters, which you can avoid by using this fast particles. Then enhancement of adhesion of the deposited film on the surface. So we have seen that surface can be cleaned, right? And then surface bonds can be broken, so the deposited film can chemically bond to the surface. And surface can be made rough by sputtering. So this would then result in, you are making it rough, so you have an interlocking of the deposited film with the surface, right? And intermixing that I already, so this is, I'll show you some examples, intermixing of the film and the substrate. So this is an example, I don't know how well you can see it here, sorry. So you can see this here, but unfortunately the top surface is, okay, so what is being done here is a trench. So this is what we have on the board. So what they have shown here is actually some film, thin film deposited. So this film, you see this red line, right? So the edge of this film, right, it goes up. Here it actually looks like with a slope of about 45 degrees. Now, how do you get this shape? At the corners. Why is it important to keep the shape? Right. So you have a sputtering of, if I take contrast between the top surface, right, here, and the corners, so you have this atoms coming and hitting. So what happens at the corners? Would the sputter rate be the same as other places? Why not? So you have seen this, for example, this can actually cause displacement damages. I'm just taking one example, right? So the particles inside would actually be pushed in. But if it is pushed this way, what happens? It just dislodges from the, okay. So on this side, it is easier to remove material. Okay, so sputter rates at these corners would be higher, usually higher than at the top. So as a consequence, you can get this, and it is important to keep the mouth of this open. Otherwise, you may have an overhang, and this would then lead to poor step coverage. So you keep the conditions so that there is the difference that you see between these two. But I would anyway, I'll post it so you can have a look. You have the slides anyway, right? So you can see this on the computer. Okay, so this can then improve the step coverage. Okay, so the other is the modification of the growing film by energetic particles. The other example is here. So this is one of my PhD student was working on deposition of aluminum oxide for passivation of silicon for solar cell applications, and she used a pulse DC sputtering process. So this is your silicon substrate, okay, and this is the deposited film. And you see something here in between, which is a slightly different contrast. So this is actually a transmission electron microgram. Okay, so you have something. You wanted to deposit aluminum oxide on silicon, but you see something in between. Okay, so what is it? So the process is done like this. You have an aluminum target, pure aluminum. Okay. And then you have a mixture of argon and oxygen. Yeah, so aluminum is getting sputtered from the target, and then it gets transported towards the substrate for deposition, and on the way it gets oxidized, because you have in the plasma oxygen as well, right? So you have this layer, and now I can look at what it is by doing X-ray photon spectroscopy, and this is actually a depth profile. So what you're doing is you take this sample, right? You have an X-ray in this case, okay, which will actually excite electrons from the core shell of the atoms, okay, and as they relax, they emit light. Okay, so you can then find out, so the emission can be analyzed to determine what kind of element is there, and also the emission wavelength would actually depend on the bonding that the element has made with other elements in the material. So, aluminum would give characteristic peaks, but if it is aluminum oxide, that peak will be slightly shifted. Okay. So, you can determine that it is aluminum and it is bonded with oxygen, and then what you are doing is you will sputter away this material and do this probing again using X-rays. So, this is what is shown here, H time as a function of the time that you are sputtering and analyzing. So, you can actually go deeper into the material, right? And we are not actually writing this as the depth. Why? I should know then, in each sputter step or H step, how much material is removed. So, that is a little bit difficult to find out because the sputtering yield of aluminum oxide, silicon and these layers could be different. Okay. So, typically you do this if it is a homogeneous material. I can easily translate this into an H rate, meaning I can find out the H rate from which I can translate this into a depth. Okay, but it gives you what is called a depth profile, though this axis is not the depth. So, what do you see here? So, this is the signal corresponding to aluminum, oxygen and silicon. Okay. So, this is silicon and this is aluminum oxide, and there is a transition layer which is called the interfacial layer, okay, and that actually contains both, meaning all silicon, aluminum and oxygen. Okay. And then from the shift of these peaks of emission, you can find out what is the composition of this. So, this will be some kind of aluminum silicate, aluminum silicate, and the composition is changing as you go closer. So, as you go closer to the interface, it becomes silicon rich. Okay. So, there is more silicon. So, this presence of this interfacial layer is very important for the passivation. And the important thing is that you see this interfacial layer in most of the deposition techniques. The silicon would easily react with oxygen. Yeah. So, if you do ALD, for example, which is a gentle process, or CVD, all cases you will find this. But here, the difference is that this is 5 nanometers. Yeah. So, this is almost about 7-8 nanometers. So, in ALD, you will find maybe 1.2 nanometer of this interfacial layer. But here it is much thicker because you are using a plasma sputtering process. So, there is actually also a sputtering on the substrate surface, mixing the deposited aluminum oxide with the silicon surface. Now, another thing is if you use different types, different power values for sputtering. Okay. So, this is actually the capacitance voltage characteristics of MOS capacitors. So, what you have here is, so what do you find here? For example, this is 500 watts deposition power, and as you increase to 1000 watts, okay, the thickness of the film increases because you are using higher power. So, the capacitance would decrease, right? The kind of parallel plate capacitor, okay, especially in this range of voltages, you can take this as a parallel plate capacitor. So, the aluminum oxide thickness is increasing, as a consequence the capacitance will decrease. But also you find something interesting between this red and the black, okay. So, between the 500 watts and 1000 watts, first thing is that the CV has shifted to the right side. Okay. So, this means what? So, you are doing a device course? Pardon? Yeah, interface traps is important, but also in this case what is happening is you have higher negative charges, higher density of negative charges in the aluminum oxide. And you are right, so there is something happening between this 1000 watts. If you look at this, right, you see the difference between the red and the black curves. Okay, see this difference between the red and the black curves. This is before anneal, this is after annealing. Okay, so there is some damage at the interface, which actually leads to high density of interface states. Okay, when you do a higher temperature annealing, then this interface states get better, and you get pretty much normal CB, but still shifted. Yeah, higher the voltage, meaning the power thickness again increases 1500 watts, right? And the CV shifts further towards the right. Okay, so this is another example. So in this particular application, what we are trying to do is to make a transistor, but not really make the transistor, but to probe whether I can use a dielectric process for a certain application. So the application is like this. You have a source, a MOSFET, and you have a gate stack like this. So you have a dielectric here, okay, and these are metal nanoparticles, and then another dielectric on top, okay. So I can store charge in the metal nanoparticles, okay. So this is essentially a flash memory device, yeah, where you store the charge in this discrete metal nanoparticles. And the objective is, why not use a continuous metal layer, is that if I have any weak spot in the dielectric, yeah, which is generated during the operation of this device, okay, so then all the charge in a continuous metal will just leak out through this point. If I have a single weak spot here, and if it is continuous, all the charge would just leak out through this defect. But in this case, the charge here, so this, if the defect is here, charge here will not leak out, because this is not continuous. There is an insulator in between. Okay. So this kind of memory devices are expected to hold the information for longer time, and I can actually reduce the thickness of the dielectric, gate dielectric. So this is the idea. Now, how do you deposit different things for this application? So what we are trying to do was to actually make this nanoparticles. So I showed you some pictures of platinum nanoparticles previously, right? So this is again an MOS capacitor that we have made with this. So this is an oxide with an silicon dioxide with an aluminum gate, okay, this line, red one. So the C, meaning this is actually the current voltage characteristics. We are looking at the leakage current through this dielectric. And now you deposit platinum by evaporation, okay. Essentially you are using an electron beam evaporator to deposit a platinum film. So you see that in the low voltage range, current has increased slightly, okay. But now if you deposit it using a sputtering technique, right, this part, the current, the leakage current has increased further. So this is now, if you look at these numbers, this is actually almost 4 orders of magnitude increase in the leakage current at low voltages. So this would be the operating regime of this transistor representative. Yeah, you are not going to go here a higher voltage range except for programming. So this would be the normal operating condition. So if I use a sputtering process for depositing this platinum, I would degrade the integrity of the oxide, right, and it would leak the charge more easily than if I use some other technique for platinum deposition. Yeah? So the evaporation is a gentler process. So this is because during the deposition of the platinum actually caused defects in the silicon oxide. So this is what we were discussing previously. So for low energies, there is no bulk damage to the film, but only the surface is being modified because the energy of these particles coming onto the surface are small. So this can increase surface diffusion due to energy transfer from the energetic particle to the surface atoms. And you have seen what this means if I actually increase the surface energy of particles so they can move faster, right? What would happen then? In the example that you have seen where the initial phase, right? If the particles move faster, what happens? So we have seen that during the initial phase you have this nucleation. Yeah. So if you have these particles moving faster, they actually would nucleate faster. So when they move faster, there is a higher chance they actually would meet other particles of which are also moving randomly on the surface, right? So this would be faster if the particles move faster. And you can also do this, the reverse process can also be happening, that decomposition of small clusters of atoms on the surface by the surface events stimulate chemical reactions and desorption from the surface if there are some volatile materials on the surface. So these things become actually important for chemical vapor deposition used in plasma conditions. So we would discuss some applications of PVD in VLSI. So the first process that we are going to discuss, meaning these are something that you can see as very easy process, right? You have a PVD deposition of titanium nitride or tantalum nitride for contact fluxes or diffusion barrier. So this we will see later on, but it's very simple. So you have a titanium target and you sputter the target using argon and nitrogen. Okay, so the the sputtered titanium will actually react with nitrogen, and then you get a titanium nitride film. And a similar thing for tantalum nitride. And copper is used as interconnect in VLSI chips because of the small resistivity. And but you need to grow a thick copper film. So what people do is usually do this by electroplating. Okay, but then for electroplating you need a conducting surface, so you actually would make a very thin film of copper is deposited using PVD techniques. Okay, and then on top you electroplate. Now this is something that we will see in a little bit more detail. So what you're trying to do is to make a contact to the source, drain and gate of a transistor. Okay, so we'll just see the process, but then I will also draw some figures on the board. So you make a transistor, right? And then you will make the source drain junctions, right, with a gate in place already. And then you have to make a contact to the source, drain and the gate without creating any short circuit. Okay? Now how do I do it? I have to make a contact to the source, drain and the gate. And for circuit designer, he should have the flexibility to apply different voltages to each of these terminals. Okay, so there should not be any short circuit. How do I make it? So let's say if I deposit some metal, right, making a contact, it will deposit everywhere on the surface. If I take a, any process, so I will deposit the metal uniformly on the surface. So you have this process for depositing films. They'll actually deposit everywhere. So source drain and gate are shorted. Okay. So she is suggesting that we should pattern this. We deposit the metal and then use lithography and etch out the metal from where you don't want it. Okay, so the other thing is lift off. Yeah. So what you're trying to do is you actually are trying to retain this metal only where you want them. Yeah, want these strips of metal, right? But if I do photolithography and if I do the lift off, again that depends on the photolithography, right? There's something called alignment. Yeah. So what this means, so when you design the layout of circuits on an IC, right, which is part of VLSI design, okay. So now I want to make the contact. What is my problem if I do lithography? So I already have this device. Yeah, forget about this for a moment. So I already have a device, and so she's suggesting that we make some photolithography, right? So this pattern is already there. I have my photolithography. There is a mask which actually contains this metal patterns. Okay. So I should then perfectly align that mask to what is already there. Yeah. If there is an alignment error, what would happen is that I may get it here or maybe here and so on. It may actually result in a short between the gate, the drain and so on. Okay. So there will always be an alignment error. Okay. So this has to be taken into account in your design. Yeah. And obviously this will depend on the capabilities of the tool that you're using for alignment, right? But also the skills of operators and so on and so forth. So this depends on the factory where you make it. Okay. So if you go and TSMC, for example, would give you specific set of design rules, which is the capability of their manufacturing line. If you go to UMC, another company that would make chips as per your design, they may have a slightly different design rules. Okay. So this is coming from alignment. Okay. But this process is a self-aligned silicide process. So which means that the process by itself is self-aligned. I don't have to worry about an external alignment mechanism to give me an alignment. So what has been done is that, so you actually make the source drain, right? So the process is self-aligned and the name comes from there. So what is actually, you have to react a metal with silicon. So that is the idea. So you are actually going to make a silicide, okay? So this would be, let's say, nickel silicide, cobalt silicide, platinum silicide, and so on and so forth. So you need to deposit the metal and make it react with the silicon. Okay. So there may be some oxide that is present on the silicon because silicon gets very easily oxidized. And in this process, you are going to do what? The junctions are formed by ion implantation, so which we will see later on. Okay. And after the ion implantation, you have to do what is called an anneal to remove the damage, activate the implanted dopants, and so on and so forth. So the surface may get oxidized, yeah, during that annealing process. So the oxide has to be removed. If you don't remove the oxide, then the metal would not react with the silicon and you would not get a silicide. Okay, so then this is the PVD process, so you would actually can do various things to remove this oxide. One is using HF. So the sample is loaded into PVD chamber and you sputter the wafer using argon to remove any native oxide. This is the back sputtering process that I mentioned. So this is, some of the systems call this as degassing chamber. It's not really a degassing, okay? But the problem is that you're using argon to sputter out something from the surface. It's not selective. It will sputter out whatever is there. Yeah, there may be some small differences in the sputter yield, but it will actually sputter out silicon oxide, silicon nitride, and whatever is there on the surface. The other possibility is to use etch this oxide using HF, so which is selective, right? It will etch on the oxide. But then, since you're talking about an ultra thin oxide, right? These days people try to integrate this with a deposition chamber. So you have a wet etching station, and then the wafer is from there loaded into a vacuum chamber directly without any human intervention. The other is reactive ion etching, may be used for removing the native oxide. So this process can be more selective than the back sputtering process. And then you sputter deposit pure titanium, cobalt or nickel as per the requirement. Okay. So what you have is this transistor. So you have your oxide and this is your gate. So you have your source and drain. So this is what is called spacer. Okay. So this is all silicon. Okay. Silicon nitride, and this is, let's say, polysilicon. So this is kind of, meaning even now people use the same process. Now I want to make a contact between this, meaning a contact to this silicon, but I don't want the contact to create a short circuit. So what is being done here is deposit titanium, cobalt or nickel as per the requirement. So you deposit it everywhere, right? So you're going to do sputtering, it gets deposited everywhere. So now you are not going to do etching of the deposited metal. Okay, this is the metal. So this can be nickel or titanium, or cobalt, or whatever you want. Okay. So you are not going to etch out. So this is already a short circuit. So I'm not going to etch out the titanium from here by using lithography and etch processes. What I'm going to do is to actually react the metal with silicon by heating the whole thing at high temperature in the range of 500-600 degrees centigrade, depending on the metal silicide formation temperature. So when I do that, what is going to happen is that the metal will react with silicon here locally, right? Create the silicide, okay? But what about the metal here? It will not react to silicon nitride, okay? Metal will also run on the isolation oxide. So here the STI, right? This is something that we have discussed previously. So there are also here some oxide on top. So there also does not react with the oxide, it reacts only with silicon. So I have this thing on the surface where you have silicide, in some regions the unreacted metal. Okay. Now if I can use some wet etch process to just remove the unreacted metal, right? So I'll be left with the silicide only where silicon is exposed. So that would be my source, gate and the drain. And the metal can be etched from everywhere. Okay. So I'll etch this unreacted metal. Yeah. So I'm left with silicide here, here and here. Okay. So this is called a salicide process. So self-aligned silicidation process. So these are some images. So if anybody works on the silicide. This is a very good source. PhD thesis from lady by name Oksana Chamirian. This is actual real transistor. So this is a TM of one of the older Intel technology nodes. So you see this transistor gate, spacer, right? This is a silicon channel region, gate, silicide, okay? And this is your source drain silicide. You don't have the metal here, and no silicide also. Okay, so this is something I already mentioned. You have aluminum oxide by sputtering, so this actually 500 watts and 1000 watts. You have a shift in the CV, which essentially means an increase in the negative charge. And this is somewhat, so this is used for passivating silicon surfaces in photovoltaic applications. It's kind of counterintuitive to what happens or the requirement in MOSFET technology. Because in, when you might have studied, I don't know, in the device physics course, if you have a MOSFET, the dielectrics you deposit on as a gate dielectric, right, in a MOSFET should have low interface states, yeah, and also what about the fixed charges in the dielectric? Should be also low. Okay. In photovoltaics, for certain cases, you still need low interface state density, but not necessarily a low oxide charge. Okay. So what you're trying to do in a photovoltaic device is you're trying to convert incident light to electricity. This is done by converting photons. So you have the photon energy, right? Photons are absorbed by electrons which are in the valence band. They get excited to the conduction band, creating electron hole pairs. Okay, and you collect the electrons on one terminal of the device, on holes on the other terminal of the device. So this is a very simple photovoltaic device. You want to collect them, which means that I don't want any recombination of this generated electrons and holes inside the device. Okay. So what is being done here is that this is a surface. To passivate the surface, you want to separate the electrons and holes. Yeah. So one technique is to actually create an electric field. Okay. So in this case, if I have negative charges, okay, what would happen? This would actually repel electrons and attract holes. Okay. So the problem comes when they are together, right? Yeah, so you're separating the electrons and holes, so this would reduce the recombination rate. Okay. So if you look at any of these recombination equations, you have product of electron and hole conservation, NP. So you're decreasing one of them. Okay, so that ends this particular module, meaning not the module, but we have in this particular part of the module on thin film deposition, we have looked at all the basic processes, the basics of plasmas, and we have looked at various deposition methods like the e-beam evaporation, thermal evaporation, PVD, and we will now see the chemical vapor deposition processes.